Here we have discussion about how to detect the modulated wave in the receiver section, and we can separate this message signal, which is important for us. So here we have two different techniques for the detection. One is the square law demodulators, another is the envelope detectors. So someone you can check as per your syllabus whether you have both or you have only envelope detector. So still, if you didn't subscribe our channel, please subscribe it and share it with your friends. In previous lecture, we have seen the generation of AM waves. Okay, so here we are going to see the detection of the AM waves. So what is the general expression of the modulated wave? That is S of t equal to AC inside the bracket 1 plus Ka into M of t into cos 2 pi ct. So where K is what? It is the amplitude sensitivity. Fc is the frequency of the carrier signal. So there we have to obtain the components. We have message components, okay, in which we have M of t that we need to obtain. Remaining other signals will be filtered out with the help of band pass filters. Okay. So first one is what we have, a square law demodulators. So name itself is the square law. So some square term we are going to obtain. So this demodulation can be achieved here by the square law device. So for that we are going to use the nonlinear device. So that transfer characteristics of nonlinear device is given as B of t equal to t. That is A1 B in of t plus A2 B in square of t. So now here V in of t is what here? Modulated wave which was transmitted. So that's why here V in is the AC of 1 plus K into M of t cos 2 pi ct. This is the modulated wave which was transmitted. So now this expression 2 we are going to substitute in the equation 1. So then we are going to expand this one. So finally we have A1 B in, so this term plus A2 B in whole square. Now here we can apply this expansion of this, okay. So here we have separated cos and remaining terms. Again, further in this section, we'll apply the a plus b whole square. Okay. So, and later we are multiplying divide by 2. So we'll get the expression for the 2 cos square theta. So 2 cos square theta expression is going to be 1 plus cos 2 theta. So that is identity used here. Okay. And here in the first term, now we are going to separate the components. Okay. So here, if you see that it is as it is what we have modulated wave, whereas in this remaining part, if you see here we have half AC A2 AC square 1 plus this is the expansion. Again, this part is going to be the expansion. So if you'll further multiply here, so this term with 2km of t, okay? So this is going to give us the desired signal in which we have message signal m of t, okay? So this is the term from the A2 B in whole square 2. So this is also called as the square law demodulators. So this signal is being extracted here by using the low pass filters, okay? And this higher order term, okay, will rise similar frequency components. So it is going to create the distortion. So higher order terms is being ignored. So that's why we're using the low pass filters. So here the ratio of the unwanted signal to the distortion is we have 2k m of t, okay, divided by ka square m square of t. So that is from here as well as from here. That is 2 upon ka into m of t. So this ka into m of t is the small, the ratio is going to be the large since it is in denominators. Hence, that percentage modulation should be limited to minimize the distortion. So sometimes if you are going for very high modulation, like we have approaching 100%, so maybe distortion is going to occur. That is meaning here. Second is the very important and popular is the envelope detectors. So question will come. Explain about the detection of the AM wave by using a square law demodulators or by using the envelope. So separate question is there. So here you have about demodulation by using envelope detectors or detection of AM wave by using envelope detectors. So already we have seen in case of generation lecture that how envelope is being formed. Okay. Here we are going to detect that envelope. So what is the requirement here that already we know that carrier frequency should be much larger. Okay, in terms of message frequency also FC should be greater than FM as well as FC should be greater than the bandwidth. So then percentage modulation should be less than 100%. Then envelope of the AM will look like a modulating wave. So modulating wave is the baseband signal or message signal, both we call. Now here, if you'll have circuit part here in this, so we have used the diode. So here modulated wave is the input S of t. That is you know about the expression AC of 1 plus Ka into M of t into cos 2 pi ft. So this is the modulated wave which is given as the input with the help of source resistance to the diode, and here we have capacitors, and this is the load resistance. So you see in the when we have this input signal like this, that is above the cut-in voltage for the positive half cycle. So during the positive half cycle, when it is higher than cut-in voltage, then diode will be in the on condition. So once the diode is in the on condition, this capacitor is going to charge. Okay. And again, diode is going to become off. Then capacitor is going to discharge through the load resistance. So there we have a discussion about charging time constant and discharging time constant that is given by the RC. Okay. So here it is going to discharge through the resistance RL. And here we are trying to obtain this envelope. Okay. That is this portion we have to obtain, and envelope is going to look same as our message signal. So that detailed operation, if you see here, okay, we are trying to extract the envelope here by the help of, since we are detecting envelope by the help of this circuit, so this is also called as the envelope detector, which is mostly used where in commercial radio, and it consists of diode and resistor capacitor filters. So now here this part we have operation. So when it is above the knee voltage, diode is going to conduct, capacitor is going to charge, and when it is going to be reversed, diode is going to be reverse bias, capacitor is going to discharge through the load resistance RL. So this is the continuous process, charging and discharging. So it is going to discharge until again it is going to get the next positive half cycle. And again, when input signal is going to become the higher than the voltage across the capacitor. Okay. For the next positive half cycle, that's input signal should be higher than voltage across the capacitor. Then diode is going to conduct, and this process of charging and discharging will be repeated. If you are going to here consider the ideal diode, so in case of ideal diode, that charging time constant is Rs into C. Rs is the series resistance that is connected with the diode. It must be short compared with the carrier time period. So carrier time period is what? Tc is 1 by Fc. So this product should be shorter. So since this is also be represented by help of tau. So capacitor will charge rapidly. So this charging time constant should be a smaller in compared to carrier time period. Where it is going to discharge through the load resistance. So discharging time constant is RL into C. So it should be very high, so that capacitor will discharge slowly. So discharging time should be more, charging time should be less. So finally, relation we have RL into C should be much greater than 1 by Fc and much smaller than 1 by that is the bandwidth here, that is the W. So in this detected, we'll have ripples. That ripples is being removed by the low pass filters. So this is how we are going to detect the AM wave by the help of a square law demodulator as well as envelope detectors. So this question is also important. Please like, share, subscribe, share with your friends. Thank you. Thank you very much.